The concept of artificial life is ancient. We see it in myths like the bronze giant Talos and the Jewish legend of the Golem. By the 17th to 19th centuries, this dream manifested in elaborate automata like the Duck by Vaucanson or Jacques Droz's writer, though some, like Kempelen's mechanical Turk, were clever fakes. Finally, Mary Shelley's Frankenstein gave us a profound, enduring caution about creating artificial beings. The intellectual groundwork began in the 1930s. Alan Turing's 1936 paper defined the theoretical limits of computation with the Turing machine. Later, his 1950 paper proposed the Turing test, asking, "Can machines think?" Simultaneously, Warren McCulloch and Walter Pitts created the first mathematical model of neural networks in 1943. This period culminated with Norbert Wiener founding cybernetics in 1948, linking control, communication, and information processing in animals and machines. This is the moment AI officially began. In the summer of 1956, a 10-week workshop brought together key figures: McCarthy, Minsky, Rochester, and Shannon. It was here that John McCarthy coined the term artificial intelligence. The conference's famous proposal stated that every aspect of learning, or any other feature of intelligence, can in principle be so precisely described that a machine can be made to simulate it. This bold claim fueled the next 2 decades of research. The Dartmouth Conference ignited an era of groundbreaking proof-of-concept programs. Logic theorist and the general problem solver proved theorems and solved simple problems. Frank Rosenblatt introduced the perceptron, the first trainable neural network. ELIZA showed that simple pattern matching could make a chatbot fool people into believing they were talking to a therapist. Finally, Shaky the Robot was the first general-purpose mobile robot to reason about its actions. The early enthusiasm hit reality. The 1973 Lighthill Report in the UK, which was highly critical of the field, triggered massive funding cuts. Furthermore, Minsky and Papert's 1969 book, Perceptrons, exposed the severe limitations of the single-layer perceptron, casting a shadow on neural network research. The final blow was the combinatorial explosion. Early programs couldn't scale beyond toy problems, leading to a drastic reduction in US and UK government funding. The tide turned in the 1980s with the rise of expert systems. These commercial applications were designed to mimic human decision-making in a narrow domain. The competitive drive was intensified by Japan's 5th-generation project, which aimed to create a new class of powerful computers and scared the West. Systems like MYCIAN and XCON became commercially viable. This boom led to specialized AI companies and a short-lived explosion in LISP machines. This boom quickly collapsed. The specialized and expensive LISP machine market failed as general-purpose computers became more powerful. The expert systems themselves were brittle, difficult to update, and expensive to maintain. Critically, Japan's 5th-generation project failed to deliver on its ambitious goals. Once again, confidence and funding dried up in a severe second AI winter. While outside attention was low, a quiet, fundamental shift was occurring. Backpropagation was popularized, allowing for the training of multi-layer neural networks. Crucially, researchers moved away from pure logic and toward statistical and probabilistic methods, think, hidden Markov models, and Bayes nets. Machine learning began to separate itself from classic AI. This shift led to key wins. TD Gammon achieved expert-level play, and Deep Blue beat world champion Garry Kasparov in chess in 1997. The Internet created the crucial third ingredient for the current boom: data. The data explosion began, providing the fuel for statistical models. We started using GPUs, originally for video games, for general computation, increasing available parallel processing power. Algorithms like support vector machines and random forests became standard. The Netflix Prize popularized recommender systems, demonstrating the commercial power of machine learning. The revolution arrived with a bang in 2012. The ImageNet 2012 competition saw the AlexNet model, built by Krzyzewski, Sutskever, and Hinton, dramatically dropped the error rate for image recognition. This was the result of combining massive GPUs, big data, and algorithmic improvements like ReLUs and Dropout. This success cemented the foundational importance of Geoffrey Hinton, Yann LeCun, and Yoshua Bengio, the recognized godfathers of deep learning. Deep learning's impact exploded across domains. Word2Vec enabled modern representation-based NLP. The development of DeepMind showcased the power of combining deep learning with reinforcement learning. The iconic moment was AlphaGo beating Liceo 41 in 2016. In parallel, new architectures like GANs for generative modeling and, most importantly, the Transformers in 2017 laid the architectural foundation for the current era. The Transformer architecture unlocked a new level of performance and scale. Models like BERT from Google and the GPT series from OpenAI from GPT-3 demonstrated exponential improvements in language understanding and generation. Scaling laws were discovered, proving that simply making models bigger resulted in better performance. This led to generative AI going viral with DALL-E and Stable Diffusion for image creation, and ultimately the launch of ChatGPT in November 2022. The field continues its rapid acceleration. We've seen the release of powerful large language models like GPT-4, Gemini, and Claude 3. Crucially, models became multimodal GPT-4v Gemini, meaning they can process and understand text, images, and other inputs simultaneously. Open-source models like Llama 3 and Mistral are rapidly catching up. We are also seeing stunning advances in video generation, Sora, Veo, and music generation, Suno, Udio. As of late 2025, the landscape is defined by frontier models, the most capable systems like OpenAI o3 and Gemini 3. We are seeing the emergence of powerful reasoning models designed to plan and process complex tasks. The focus is shifting to agents and autonomous systems that can execute multi-step tasks. Financially, the scale is staggering. The market cap of leading AI companies is now estimated at over 15 trillion combined. The current, sustained boom is not a fluke. It is the result of three foundational breakthroughs converging. First, compute. Moore's law combined with GPUs, TPUs. Second, massive data. Internet-scale data and labeling. Third, breakthrough. Algorithms, deep learning, transformers, and alignment techniques like RLHF. Finally, this convergence has been accelerated by an unprecedented amount of money, trillions invested since 2020. With great power comes great responsibility, and AI presents significant challenges. The computational scale leads to immense energy consumption. The power of generative models fuels misinformation and deepfakes. There is a massive risk of job displacement across industries. And fundamentally, we must address alignment and safety to ensure AI systems act in humanity's best interest alongside the growing concentration of power among a few companies. Fortunately, research is focused on balancing these risks. We are developing strategies like using renewable compute and increasing the efficiency of models. We can combat deepfakes with watermarking and provenance tools. The challenge of job displacement is addressed through investments in retraining and education, and the fundamental problems of safety are the focus of intense alignment research and the promotion of decentralized, open-source models. Looking ahead, the next decade will be transformative. The AGI debate is real, with the median expert forecast giving AGI a 50% chance by 2030-2035. We anticipate seeing AI agents running entire businesses or complex systems. We expect an unprecedented acceleration of scientific discovery, following the blueprint of AlphaFold. Finally, the synergy between quantum computing and AI could unlock computational power currently unimaginable. Thank you for watching, and see you next time.